Okay, our next speaker is John Kolm, who's the CEO of Team Results USA, a company that specializes in the practical application of nonlinear gaming and new approaches for team dynamics for the corporate and government world. And his staff are either workplace psychology specialists, technical setup specialists for serious gaming environments used with clients. John has a psychology degree from the University of Melbourne, an MS in math from the National Cryptographic School, and is interested in nonlinear dynamics and team cognition as it applies to the workplace. He's also an award-winning author and has had multiple experiences with intelligence agencies.
Thank you. This is Martini. You just really can't beat speaking in Las Vegas. That's great. Well, hi, folks. I want to talk to you about a series of experiments that we did and some conclusions that we reached. I know I have an Australian accent. That said, I speak to people all the time. But if I am going too quickly, please don't be hesitant. Just put your arm up and wave frantically and I'll slow down again. We want to announce a new model for the way in which teams and groups work together. This is something our company's been working on, but it's a partnership with UCLA in the person of Ron Stevens and Tricia Galloway and their crew, and also a company called The Learning Chameleon, which is also connected with Ron. Because these talks are short, it's a good discipline. It means you have to cut to the chase, so this is the chase. I'm going to cover the model first, the way in which it was derived second. So let's take a look. Those with math training will immediately recognise this as a hidden Markov model, a Markov transition model, but it doesn't matter what it's called, and we don't need to get into it too deeply. What we have found, though, is that to understand the way in which teams and groups work, evolve, and grow, five states of being for the team are both necessary and sufficient. Let's go through them. Some of them are very obvious. The evidence underlying this, of course, is neurodynamic. Let's start with the most obvious one. The good old dominant state there. We've all seen this a million times. One leader and everybody else pretty much follows and does as they say. Next, perhaps logically, the dyadic state. Here it's not one leader, it's a leadership clique. It's a small group of leaders, and everybody else pretty much does as they say. Anyone with any time or experience in the workplace has seen that a million times. Let's move on. Where is the outlier got to? There they are. This is our friend the outlier. This is the opposite of dyadic. Here, the whole team is pretty much on song. The level of engagement is pretty similar and pretty good across the group, except for a small subgroup. And that small subgroup is totally disengaged and disenfranchised. And we've seen that many times as well. Two more states to go. Col means collegiate. This is the state where engagement, we looked at workload as well, but I'm just going to talk about engagement. And the results for workload are very similar. This is the case where engagement is uniformly high across the group. It is the mythical perfect team scenario that we all think is ideal. It's actually not, as one of the things we discovered. It's a transitional state. But it's the case where everybody's working together very well, to the degree where at times it's almost hard to tell who the designated leader is supposed to be, if there was one. And finally, at the opposite end of the experiment here, we have dormant. That's the exact opposite, of course, of collegiate. Everybody in the team is completely zoned out, and engagement is uniformly low across the team. Well, what models are being used now? There are a few, but this one is by far the most, if I may use the word in a different context, dominant. There is no MBA school in the country, no leadership course in the nation that is not teaching the Tuchman stages of team development. This was a paper that was originally written in '65 with a follow-up adding that fifth stage, which people don't often use at the bottom in '77. Tuchman, legendary American psychologist and the author of the model. Forming, storming, norming, performing. A good old industrial age model with 4 states and 3 transitions organised canonically so that people plod along like John Wayne's trusty old horse from one to the other until they get to the end. It's a great model, but Tuchman didn't have the advantage of somebody like Professor Stevens and his wizardly team of neurodynamicists to help us look at what the brain really does. So we think that this model is ready for a bit of a refresh. It has been a very long time. One more point I want to make before we move into some of the evidence behind it. The Tuchman model, in addition to anything else, is a Gestalt model. which is just a fancy word meaning everybody's the same. So for example, when we say the team is in the forming stage, what we mean is every individual in the team is in the forming stage and therefore the team is in the forming stage. It turns out though that to accurately model the evolution of groups and teams in the real world, again, a model that's both necessary and sufficient out of the 5 states, has and requires only 2 states that are Gestalt states, and the other states are non-Gestalt states. Let's begin with the Gestalt states, and those of course are quite evident. Here we have collegiate. That's a true Gestalt state. Everybody is pretty much the same in the Tuchman sense. And at the other end of the spectrum, of course, dormant. Once again, a true Gestalt state. Pretty much everybody's in the same boat. For these other groups, though, where there's an outlier, or where there's a dominant, or where there's a dyadic, that is not true at all. We have to take the fine structure of the team into account. Not all people in the team are in the same state of engagement whatsoever. We think that that combination, that juxtaposition of Gestalt with non-Gestalt states, of linear with non-linear states, is responsible for much of the astonishing speed and flexibility and adaptability that we see and measure in work teams as they move. One of the many issues that I've always had with the Tuchman model is it's far too slow. It's not what I've observed in 20 years of working with senior teams around the place. I've observed people working very quickly and jumping all over the place. So it's very gratifying to find a model that reflects that and is scientifically verifiable. We did the same thing most of you have done, which of course is that we used this is advanced brain monitoring equipment, and we gave them a problem to do. Here they're moving, mathematicians will call this device a turtle. To the rest of it's a toy car. And we had them move a toy car around an area and set off some little explosive devices. And we took away the controller and instead provided them with this 4-controller system so that the team as a whole has to move the car around and set off these little charges. That is incredibly difficult to do. I won't go into it. It's a tremendous amount of fun, but it's incredibly hard to do. And it requires astonishingly good coordination across the team. That's Tricia Galloway monitoring the information as we were doing these experiments. And here you see the little toy car, some chicanes, which of course are there for the express purpose of being in the way, and the device here which they're going to set off. When the team's getting their act together, it looks something like this. Watch closely, something cool's about to happen in a moment. They've almost got their coordination working actively, and wacko. And there's their feedback, and they've set something off, and as you can see, they're very happy about it. So now to the science, and this is something that you saw in the last talk, which saves us a bit of time, which is great. We have been watching, and again, I'll talk only about engagement. So you're looking at engagement here across 4 people. It's mixed in, incidentally, with some other stuff that's to do with 6 people shortly. But we're looking at engagement across 4 people over a total of 25 popular symbols for some definition of the word popular. I invite you to amuse yourself by reinventing the taxonomy that we developed for these systems that led to the 5-state model that you've just seen. A couple of parts of it are very obvious. For example, that's clearly a dominant symbol there. There's one person with high engagement and the rest are following the leader. Down here, this is pretty equally clearly a collegiate state. Some of the others require a little bit more thought. But that taxonomy is persistent, it's necessary, it's sufficient. It works across a variety of tasks, not just the one you saw, and across a variety of groups in a variety of modes, as you'll see. So if we do the familiar state transition diagram, just the phase transition graph, and we choose our colourings according to fairly standard methods. Here, looking at random data, that's just what no results would look like, just for comparison. And here, up here, of course, we have, well, you may not be able to read it, so not necessarily, of course. It says easy problem. So this is an easy version of the problem you just saw. As you can see, quite a few states are along the diagonal. These are states transitioning to themselves, but there is some interesting off-diagonal structure as well. Now let's make the problem a little bit harder and look at this. The level of data compressibility immediately increases. In other words, the level of simplicity, the level of organisation within that rather complex and baffling structure suddenly, becomes far crisper. That said, it's still a fairly baffling mix of red bits here, there and everywhere, and there's no immediately obvious thing that pops out. And what it reminds me of mostly is Crick and Watson staring at the X-ray crystallography results decades ago, thinking something cool is happening here, but this is complicated, surely there's a simple explanation. Well, the simple explanation is a 5-state Markov model. So getting back to these things again, all we're doing is really replacing those graphs with counts and obviously accreting the counts by taxonomy in the model. So let's look at some real life situations here. We're going well for time, which is great. This is the easy minefield scenario once again. So this particular case, by the way, this is a team of tertiary educated adults that we're looking at here doing the easy minefield. So they spend most of their time in outlier, and next in the pecking order is dyadic, and they spend a lot of their time bouncing between outlier and dyadic. And in the math biz, we refer to these lines as edges, or sometimes vertices. So this is a high priority edge. Also note as well that with a hidden Markov model, not only can you transit from any one state to any other, but a state can also transit to itself. That's perfectly allowable in the Markov model. So this is populated with probabilities, and we have found that clear patterns emerge and that those patterns are diagnostic, and you're about to see that.
So now let's take a look at it diagnostically. Here once again is the easy minefield case where the commonest visited state is outlier, followed not too far behind by dyadic, and you'll notice that there's that rather rare transition from collegiate to dormant or dormant to collegiate. It's bidirectional and rare. Now let's make the problem harder. Let's go to the hard minefield. Watch the change closely. Outlier and dyadic switch places. Dyadic is now the most common state. Outlier is next, but dominant is in play as well. And take a look again at that transition. What was a rare transition is now a never happens transition. It's a forbidden transition between collegiate and dormant in either direction. That transition goes away as the problem becomes harder. Why does dominant come into play? Well, we think that that's because with a harder problem, there's more of a need for an individual to take charge from time to time and say, hey guys, let's do it this way. We also think that outlier and dyadic switch places because, again, there's a greater advantage now in a small group of people communicating very intensely with the rest following on as they get to the harder parts of a harder problem. Now let's look at an entirely different problem. Here we have some college students in class. This isn't an experiment that we ran, this is just a standard class in a standard college. Perhaps not too surprising that the most common state is the outlier state. That's the state where most students are more or less hooked in, but there is a group that is disengaged. Interestingly, the dormant state, the one everybody jokes about, where the whole class is asleep, is quite rare. The commonest state that shows disengagement here is the outlier state. And then occasionally we had visits to the dominant state, and we surmised that this is one student asking a question or talking directly with the professor. Now let's look at a team operating a nuclear submarine. You'll see immediately this is very similar in a lot of ways to the mine clearance vehicle experiment that we did. The most common state here is the outlier state. There's a small group that's a little bit disconnected from the rest of the team, and the rest of the team working on the main game. But the dyadic and dominant states are also pretty common. Note again that forbidden state. It was there in the minefield. It's here again with the nuclear sub between collegiate and dormant, and there is a new forbidden state for the nuclear subteam that also appears between collegiate and dominant. Well, what does this all mean for the future? We think it means three things. First of all, we hope that MRI-style diagnostics are somewhere in our future. In other words, we will have pictures, just as doctors do, for a healthy team, a not healthy team, an emergent team, a mature team, a team of experienced, a team of inexperienced people, the kind of result we want, the kind of result we don't. As the methods of monitoring become easier to use and the library of diagnostics becomes smoother and smoother, we hope to get to a state where we can find out very insightful things about work teams very quickly, both in the lab and in real life. And that leads us to better taught models. Models that respect the new world and the new understandings of nonlinear dynamics, don't though in the process entirely forget everything that we knew about linear dynamics, integrate the two, and just give us a much better model of what real teams really do in the real workplace. And finally, we hope, flowing from that, that there will be predictive value at work. That's the holy grail of any scientific model, of course, to give you some idea of what might happen next. That is what Markov models do particularly well, and we anticipate that because this is really a simple model, it's going to be fairly straightforward in a lot of cases to make some pretty good guesses at likely transitions, likely next states, likely futures for a work team. These are some of the clients that our experience is based on when we talked about 20 years of experience, and this is just a shameless plug for a book I wrote some years ago, which is on the same subject, but it's a popular exposition. If you want to get in touch with me, with anybody at Team Results, or for that matter, through us with the UCLA team, please feel very welcome to use this information here. Thank you for your time, and it's been a pleasure talking to you.